So today I'm going to be presenting this work that we've been working on for now almost a year, I think, so quite a substantial amount of time. I think you're pretty familiar with the context, which is that essentially internet access provides revolutionary opportunities for people to improve their lives, for society to progress. And within the Sustainable Development Goals that have been set by the UN, there is this one that specifically refers to internet access, so SDG 9C, where we strive to provide universal and affordable access to the internet. There's also been this kind of commitment from the UN Broadband Commission recently that they want to kind of up the speed target to 10 megabits per second per user, which I think is very high. I would normally say that we want to be delivering 1.5 or 2 meg per user in the hardest to reach areas, because at the end of the day, you've only got limited capital to invest. So whatever decision you take here for delivering the speed target, you're going to keep some people offline, unfortunately. So really what I'm trying to do in this talk today is to present analytics which can inform this particular potential decision that people want to take. So there's 3 billion people without access to the internet across the world. And if we look here at this kind of global graphic, which represents how people basically speak to Facebook servers, so that will also include Instagram and WhatsApp as well. Then there's lots of 4G connections across North America, India, China, Japan, South Korea, lots of 3G generally across Europe, Latin America, and then lots of 2G, we can see the red, particularly in sub-Saharan Africa. So these are the areas where we really need to improve the existing level of digital infrastructure. Okay, so what I'm going to try to do today is to present analytics which can help us understand how we do that on a commercially viable basis. This isn't really very well understood, and a lot of the work that most people do, and the work that Zoraida and I have done in the past, don't really consider the demand side dynamic. We haven't always kind of put values on how much people can pay and look at the kind of balance sheet model for where you get viable services. So really I'm trying to pick up on the shortcomings of the previous analyses. And as you know, the aim is to try to deliver broadband universal access to the developing world. So the objective is to quantify how potential judicious government policy choices could help to reduce the costs required to deliver the infrastructure. Okay, and there's a variety of different ways that we can do this, and we're going to assess the potential technology choices, as well as assess different options for infrastructure sharing, and also look at things like spectrum pricing and taxation, which government have the ability to change essentially. So we want to understand how these might affect the rollout of new technologies. So that's the kind of high level aim. I'm going to get into the method now. So essentially, I want a model that's spatially disaggregated to the local level, so I can say I can have a good understanding locally of how much demand there is and how much existing infrastructure there is in certain places. But I want to do that globally. So there really isn't any sort of existing capability that can allow me to do that. So I had to develop my own code base, which basically allows me to estimate demand at a very local level, and then also basically estimate least cost network designs for different technologies. And then when you do that, you're able to bring together the demand side and the supply side into a set of analytics. And then we're able to use those analytics to assess how effective different decisions potentially are at the national level. So this is very much aimed at governments, essentially. Okay, so within the method, I have these 3 different steps, and I focus on clustering countries. So that's to look at countries which are kind of similar. Then we're interested in doing some detailed country modeling to understand what the cost per smartphone might be, or the cost per member of the population. And then I want to be able to generalize those costs within each cluster to all the other countries. And that's how we basically get to produce an estimate for all of the low and middle income countries across the world. So how do we start by doing this country clustering? Well, essentially, I take data for those factors which affect the take-up and rollout of cellular communications, internet access in this case. So that's GDP per capita, the population density, and the 4G coverage. I chose 6 clusters basically to cluster the countries on for a variety of reasons. So this reduced the variability to a sensible level, while also balancing out the fact that if you have lots of clusters, it becomes increasingly harder to visualize the results. So this was a way for us to kind of cluster countries together in a sensible way, and then have kind of generalizable costs across the clusters. So I've actually just ranked them over here from cluster 1 to cluster 6 based on GDP per capita. So in the highest group, we've got Mexico, Brazil, Argentina, China, Russia, the Ukraine in this particular group. And then at the other end of the scale, in basically the lowest category grouping, we have countries like Malawi, Democratic Republic of Congo. So there's there's a much more challenged environment for deploying internet access technologies in these countries. So that's essentially how I came to the country clustering. Then within those country clusters, what we need to do is select representative countries. So we actually ended up with 8 countries in the end. And that's because we had a set of countries who were really interested in the work and they wanted to engage. So we ended up with 2 countries in each of the cluster 1 and cluster 2 groups. So Malawi and Uganda were very interested and wanted to be involved. Senegal and Kenya in cluster 2. And then cluster 3, we had Pakistan, cluster 4, Albania, cluster 5, Peru, and cluster 6, Mexico. And there's quite a substantial difference in the geographic conditions and the socioeconomic conditions between these different countries. So really quite low income per year in Malawi, below $400, moving all the way up to Mexico, where it's under $10,000 on average, but quite substantially higher. And then the area, and this affects the population density, obviously, is quite drastically different. So Malawi is quite a small country in comparison to Mexico, which has absolutely huge landmass. So this is really kind of challenging to kind of capture all in one analysis. But that's why we did this clustering approach, so that we could try to get countries into each of these clusters which had similar characteristics. I think one of the challenges that we did have was with the cluster 3. Cluster 3 basically has India, Bangladesh, Pakistan, Vietnam, the Philippines, so countries with incredibly high population density, which is challenging to deploy cellular communications for, but also it's quite challenging to model. So the computation time for doing India or Pakistan is substantially longer than all the other countries, because we have to extract the data from the population density layer, and that's just a long process when you've got so many people. So they're the countries that we decided to pick. What are the scenarios that we're going to run? Okay, so essentially we're going to test a set of strategies, and these strategies focus on the technologies that we can pick. So whether it's just basic LTE 4G, whether it's 5G non-standalone. So this is basically, this is the 5G spectrum running over a 4G core network, or whether we move all the way to 5G standalone. So this is the kind of all the fancy hyped technologies that you hear about focusing on low latency communications with edge computing fall within this category. One of the major challenges, though, for governments is, well, do we encourage fiber backhaul to be deployed, or do we encourage wireless backhaul to be deployed? So if you build a cell tower, that's great, but you've got to connect it to the internet, and that's often the challenging part. And in rural and remote locations, actually, you have to spend a lot of money on the backhaul component. So that's why this bit is really important. So they're the technology options. For business model options, we're testing a set of infrastructure sharing approaches. So for baseline, we just have no infrastructure sharing. We just model a hypothetical mobile network operator. Whereas for the other options, we have passive infrastructure sharing. So that's where they share the non-electronic components of the site. So it's like the compound and the tower structure, but they don't share the antennas. Active infrastructure sharing is also called a multi-operator radio access network in Iran. So that's where you share the electronic components as well. And then we also test a shared rural network. So that's basically saying we want competition everywhere, except in those locations where we think it's going to be challenging to deploy, in which case we're going to let you use a multi-operator radio access network. and we wanted to test what the cost would be there. And then for the policy options, we take baseline spectrum prices from 4G, and then we vary them essentially. Taxation, this is focusing more on just general taxation. We don't get too explicit here because it's a large model already, but just think that this represents corporation tax essentially. And then we also want to, and this is kind of the main point of this work, actually quantify the required state subsidy to deliver universal broadband across these countries. So the technology options, so just imagine that for a standard 2G, so that's voice, or 3G, that's kind of low data rate data communications, you have this distributed cell structure here. So you have a tower, and then you have a box at the bottom, and in that box you have a bunch of electronics that keep the processing equipment cool, essentially. And that's connected back to the internet via backhaul. Then for the kind of 4G or 5G non-standalone approach, we just have a very similar structure. The difference is that you just have remote radio units mounted underneath the antennas because it reduces the noise essentially, and provides higher capacity overall. So this is essentially the type of structure that we would have. So if in these strategies, we would be upgrading these other cell towers to this structure. And then for the more kind of futuristic 5G bonanza, you would expect something that might be cloud-based radio access network, and it might access all of those things that people talk about when they mention 5G. So the 5G jargon, which is network function virtualization, software-defined networking, low latency communications, edge computing. So we basically just bucket all of that into this one strategy. So just imagine this is commercial, off-the-shelf processing equipment like you would have in a data center, but you just have a small data processing area, which might be shared across 7 other cells, 7 other sites. And essentially they're all fiber connected, and you have all of your processing equipment within this particular item of equipment, which is on one of the cell sites. So I'm not going to go into massive detail about all of the engineering and computer science for how we dimension this. It's in the paper, and I can talk about that in the Q&A, but given that this is more kind of a social science audience, I've kept these strategies kind of high level, I hope. So just think of this as futuristic 5G. And I mentioned before about the business model option, so the infrastructure sharing. So if you're just building your own network, you would build your own core network, your own radio access network, you buy your own spectrum. But then that would be different if you basically had passive infrastructure sharing, which would be some of these options over here. Or if you had an active infrastructure sharing approach, which is a multi-operator radio access network. So here you would share a lot of the electronics and the site. Or if you had a shared core network where you would basically just buy your own spectrum and share the rest with other competitors. So these are a variety of different options which are reasonably well written about in the literature now. So I hope you can see this okay, but this is basically the model that we're going to, this is how we build the model essentially. So this is the demand module. So I have the WebEx, oh, there we go, it's gone out of the way now. In view of mine. So basically in the demand module, what we're doing here is we're taking the number of people in each local area, we're taking an expectation for how many phones we have in each local area, how many networks we think are operating there, to basically endogenously estimate how many users we think are on that network in that local area. So this thick black line here represents endogenously determined variables. Essentially, then we're able to estimate the data demand, given some expectation about how many smartphones there are, some expectation about how much capacity we want to deliver per user, and then some expectation about how many people are using the network at each time. And when we know how many users are on the network, also we can estimate the revenue, which we can do by having expectations about the average revenue per user. We can then take that data demand forward, and then we can basically dimension a cellular network based on how many existing sites are there, how much spectrum there is available, what technology we're using, and then that can give us an understanding for how many sites we need to upgrade and how many new sites we need to build. And that provides us with some sort of grasp of the network cost. And then finally, we have this kind of assessment module where we have this production function for a cellular operator, which includes the cost of the network, the cost of the spectrum, some profit margins, some taxation that they would end up having to pay. We use this kind of user cross-subsidization approach. So we assume that there's a coverage obligation, which is kind of pushing the available capital out to rural areas in order to cross-subsidize from highly profitable areas to less profitable areas in order to roll out this infrastructure. And when that cross-subsidization runs out because there's no more capital left in the system, no more revenues to reallocate into infrastructure investments, then basically you need a state subsidy. And that gives us some understanding of what the total cost could be to deliver an area. So I hope that I know that's complicated, so I'm going to break that down quickly now. So essentially, we're going to use the data that we've got to estimate the number of users on the network. There's some math here. It's not particularly complicated. In fact, it's just basic arithmetic for each area, essentially. So we get the number of users, we get the demand per area based on the amount of capacity we want to deliver for the different user capacity scenarios, which I'll talk about later. And then we sum up the revenue, basically. So how many users there are and how much average revenue per user they actually spend per month. Mobile subscriptions, essentially we forecast the take-up rate for these countries based on the GSMA data up to 2020, and then we forecast it forward. And then I also take a forecast for the smartphone adoption rate for urban and rural areas. So these are exogenous scenarios which we kind of plug into the model for how many people we think there are going to be who will take up services over time. The average revenue per user is really hard to estimate because it's not available information. It's commercially sensitive. So what I do is I take the nighttime luminosity. So, you know, we have global data layers available from NASA, and we know that the luminosity of light emitted from certain areas is highly correlated with per capita income and wealth, because, you know, there are streetlights and you can afford electricity. So this is a good predictor of who will fall into the different average revenue buckets. And we basically allocate consumption tiers, which are built around the GSMA ARPU data, which they provide. And then we're able to build these for each of the countries, essentially. So there's three main ways to enhance the capacity of a cellular network. You can increase the spectral efficiency. So that's basically, if you have a road, imagine that you have smaller distances between the cars are the packets. So if you have a more efficient connection, then you're able to transfer more cars over the same lane, essentially. Whereas if you add more spectrum, that's like building a new lane on the side of existing roads. So you've got more capacity overall on that one link. Whereas if you actually build more cells, that's like building new roads altogether, essentially. So there's these three different options, but they all come with limitations for how you actually do that in reality. So they're technically challenging to increase the efficiency, spectrum is scarce, and cells to build are expensive. So on the supply side, how do we estimate the capacity for those locations where we don't have geographically explicit data on the number of sites? Then we take an estimate of the number of sites based on a disaggregation, which I carry out based on population density. So if you're going to deliver a cellular network, you would first start building in the highest population density areas because that's where the most demand is. And that logic can be used to develop a disaggregation. I then use a system model essentially to estimate the network spectral efficiency for the number of cells in an area based on the number of sites. And then when you have that for each frequency band, given some spectrum bandwidth, you can estimate the capacity of an area. Okay, so this is the technical engineering bit. I'm not going to go into too much detail about it. You can ask me in the Q&A if you want about it. This is reasonably well published. We put this out in other papers. Essentially, you have different capacities based on the frequency band that you have to use. And we have to try and approximate how efficient those bands are based on distance from the cell. And we transfer that into kind of a network density, which relates to a capacity. And that's kind of the basis for how the model works. then I developed these least cost designs. So essentially, what you're looking at here is the fiber backhaul routing for all of the countries which we assessed. So the existing fiber is in black, and then we basically had to connect new fiber links in.
May I interrupt? Excuse me.
Certainly.
I think the slides are frozen. I mean,
oh, okay.
The question is, where should we be? Because I think in the meantime, I thought you just described the boxes. But so we are on the demand module?
No, I've gone way ahead of that. I don't know.
That's what I thought. I thought we're like basically without giving us, because you said it's too technical kind of thing. You wanted to spare us from this. So it was basically all the time just one. Yes. So we were basically stuck with the top one.
Oh no, I'm sorry.
No.
So essentially, what I've been through is I'm worried about time, Volker, because we've only got like 20 minutes left. So I assume you will need to go at the end of the hour. Is that correct?
I have some extra time, so I don't know how the audience is. I mean, the research group, they have my permission to stay longer, of course.
Okay, well, I'll try and go as quick as I can. So this is basically how the model fits together, and you've heard me qualitatively talk about it. I'm not going to go back over it now in detail. And I've talked also about how we plug the equations together, how we forecast demand, how we then estimate the average revenue per user based on nighttime luminosity, how we build out the capacity of a cellular network.
Yeah, I was thinking you had like a more puristic approach to presenting today.
So yes, this just basically is emphasizing those different frequency bands based on the different distance. And these are the least cost designs which I got to. So essentially, we have existing fiber networks. We need each region to have a fiber link. We need to build that. That's the least cost design in red. We have new fiber nodes that also need to be built, which are kind of the local serving fiber, which are in yellow, and any sites that we build can now connect back into this network, basically. Okay. Costs are boring. I don't really want to go into costs in too much detail. I just want to point to the fact that in some of our work, we've used kind of assumed costs or one or two citations. And actually what I did was I went over a whole load of publications which use costs, and I reported what they say for equipment, for the site build, for the installation, and then I used the mean cost across all of those studies. And then the same for the OPEX down here for the site rental, the backhaul cost, the operation and maintenance, the power, et cetera, et cetera. And this is broadly consistent with the kind of cost structure which I built originally before I kind of validated it in this way. So this is quite European centric, though, quite high income country centric. So you know, there's questions over how applicable those costs are for other countries. Spectrum costs, well, we had a spectrum database essentially where we analysed the costs of the spectrum licenses in all of the 6 clusters for coverage spectrum, which is below 1 gigahertz, and capacity spectrum, which is above 1 gigahertz. And essentially then I get the dollar cost per megahertz per member of the population in each of these countries, which forms the baseline for the analysis that we do. And in the assessment module, we basically get the cost by basically saying, well, the network cost is the radio access network plus the backhaul plus the core. The spectrum cost is the cost per dollar, so the dollar cost per megahertz per member of the population for each frequency, multiplied by the bandwidth that you have.
May I just have a question related to the spectrum cost? Mm-hmm. Because the first question I have, is there some scarceness in this context, in these countries, regarding to these spectrum capacities, or not? If there's no scarcity, I would expect there's not so much scarcity in this, in some of the areas of the countries. Then I would say the social optimal costs are zero.
These are the costs from the previous spectrum auctions, so they're revealed preference.
That comes from the auctions, but even a kind of viability of what they are doing with the upgrading of the network, that it is viable to invest in this, or is it also depending on the amount of subsidies? I mean, someone has to finance it.
Yes, I agree. And the point you're making is exactly the point of the paper. But I think if you're sat and you're a government operator, you're a government decision maker in Malawi or Kenya, your spectrum revenue is the time that you're able to bring in a huge amount of money, which you can then spend on social projects. So this is basically the logic for trying to pull in lots of spectrum revenue, essentially. Okay, so I'll return back to spectrum costs because one of the main findings is about this. But the point is that we just took the past costs that were used and then we basically, these reflect the net present value, taking into account the length of the spectrum license and the fact that there are some upfront fees and long-term fees. So we have a spectrum database that helps us yield these results, basically. So, yes, so this is how we basically calculate these costs. And we also add on a taxation rate because they're additionally taxed, the operators, and they're also going to be raising money on the private market and taking a risk. So we include a profit margin for the amount that they basically spend. So that's used. So the tax rate is dependent on the scenario. It's about 30% on average. The profit rate, we allow about 20% based on the network cost, which comes through to about 10% overall by the time you take everything into account. And actually, the other two people I work with are proper economists. I don't class myself as a pure economist. And the way that we've conceptualized the costs here is to focus on the societal cost, which is basically the cost to the government and the cost to the private sector. And the cost to the government is basically how much they have to spend on the subsidy for rolling out the network, minus any revenues they gain from spectrum and tax. And then the private cost is basically the cost of the network, administration, which is usually about 30% of the network cost, the spectrum fees, any tax they have to pay, and any profit. So we need to kind of portray this in kind of the societal cost overall, and that's how the results are essentially presented. So we take into account the fact that government basically has inflows and outflows. So the results. So I'm presenting here results for 3 different scenarios. So we go from 25 megabits headline speed in scenario 1 up to 400 megabits per second in the most ambitious scenario. And in rural areas, we're aiming at 2 meg here in this S1 scenario, 10 meg in rural areas in S2, and 30 meg in S3. So really quite ambitious. So we're really most interested in the S1 and the S2 scenarios. We then have these strategies. So we have 4G with a wireless backhaul, 4G with a fiber backhaul, 5G non-standalone with a wireless backhaul, and 5G standalone with fiber. And then we have all of the social costs, essentially, and we can start to see patterns accruing within the country costs. So, for example, 4G is usually cheaper in those countries that have already managed to roll out a lot of 4G because that's already a sunk cost. Whereas those countries maybe where you've rolled out a small bit of 4G, but you've still got 80% of the population to cover. Sometimes 5G actually can be cheaper if you're using a non-standalone approach because it's more efficient and therefore you need fewer sites. So these are the costs basically for each of the countries that we analysed. I'm going to present these in terms of the actual percentage of GDP because that's in some ways more relevant when you do these cross-country comparisons because the cost of investing, for example, 35 billion to Mexico is actually a lot smaller relative to what 1.5 billion might be to Malawi, for example. So these are the headline costs, which I'll return to later. So what's the cheapest technology to deploy in each of those settings? So we have the countries on this furthest left column here. We have the scenarios, and then we have the baseline strategy, which is just everything business as usual. And then essentially we have the infrastructure sharing options, the spectrum pricing options, the taxation options, and the lowest, which is just where we turn everything to be the lowest cost option. And what we found, which was kind of interesting to us, was that so in Malawi, 4G is the cheapest at this level because is quite a small country. 5G really becomes a lot more competitive when you have a lot of people, essentially. So particularly for Pakistan or Kenya, where you've got some huge populations, 5G can be a lot more efficient than 4G. So that kind of gives a bit of explanation for why we're ending up with these different outcomes in terms of the different technologies. For these more advanced countries here, they've already deployed a lot of 4G. I mean, the remainder that they need to actually cover is really small. So it's very cheap for them to deploy just 4G in those areas, as opposed to an entirely new 5G rollout. The issue, though, here is that the choice of technology that they might end up choosing also relates a lot to industrial strategy. So just because 4G wireless in our cost minimization framework is cheapest here for Mexico, the likelihood is that they're going to go for 5G, and they're unlikely to use 4G as their main kind of technology to deploy. So there's some larger questions around how you kind of interpret the results here based on the country context. So infrastructure sharing, what we find is really quite a dramatic fall in costs from the infrastructure sharing options. So somewhere between 15 to 70% of the cost, depending on the scenario, can be saved through moving to increased infrastructure sharing. So particularly the shared rural network in countries where you've got lots of rural areas is a really efficient way to deliver the infrastructure cheaply. So at the moment, this is just focused on rural areas. In future work, I will make this focus just on those unviable locations where you're unlikely to be able to roll out the infrastructure within the existing kind of framework. And that's because, there's this trade-off between competition and consolidation, and this is going to keep coming up as I move towards the discussion. So spectrum is quite a significant portion of the costs in many countries. It can be up to 30% of the cost. So the actual pricing of the spectrum has a huge impact on how much cash is then eventually available to roll out to those additional areas. And so I'm just emphasizing that here based on the total cost structures that we obtain for all of the different countries across the different scenarios. We can see spectrum, which is orange here, is particularly high in some countries. And the reason why this matters is that our results essentially show that if you have high spectrum prices, you end up with a much higher societal cost, essentially. So there's very little benefit if you're in a market which isn't viable overall because you've got low demand from ramping up the spectrum costs, because what we basically find is that for every $1 that you take in revenue from spectrum auctions, you have to pay out $1 in subsidy to roll out to unviable areas. And that's one of the main conclusions which we've taken from this piece of work. So the social cost in general. So before we were just looking at the baseline costs across all the different technologies. Now I'm comparing for 5G non-standalone with a wireless backhaul between the baseline cost and the lowest cost. So this introduces all of the policy saving options that can help to reduce the cost. And really it's quite substantial. So I mean, if you just take Malawi here for the least ambitious scenario using 5G non-standalone, it could be about 1.5 billion to connect those areas. Whereas if you allow all of the policy options to kick in, you could end up doing it for a fraction of the cost. Okay. And when we then compare those scenarios, essentially, so the baseline against the lowest in terms of the population that you can viably cover, when you implement the lowest cost solution, you can start to get above 90% population coverage in most of the countries that we're focusing on here. And that means that basically if you relax the regulatory framework and the spectrum costs and the taxation rates and the infrastructure sharing, you end up needing to invest more through subsidies as well. The market, providing you're regulating the market correctly with a coverage obligation, then most of the market should be able to plug a lot of those coverage gaps that you might end up having. So what are the costs for the whole of the developing world? So what we have here are each of the scenarios and strategies. We have the total cost for all countries around the world, and then we have the 10-year GDP share. And essentially what we're looking at for 4G wireless is about $500 billion in the baseline case. in order to plug all of those areas currently not being served in the minimum threshold scenario. And if we implement all of the policy options, then we can reduce that quite substantially. So this figure here, the baseline, matches up with the other UN Broadband Commission analyses that have been done. What's new is our approach to the policy options, which basically can potentially reduce the cost really quite significantly. And then we've expressed those costs here in terms of the GDP share over 10 years. So you would need to be investing, 0.2% every year in order to do this scenario here, whereas that drops really quite significantly when you move into the lowest category, and so on and so forth for all of the costs. I think the important one here to look at is the 4G wireless row, which is about $500 billion, and then the 5G non-standalone one here for the more ambitious scenario, which is about 1.4 trillion, because these are the most plausible options that we would likely see between the different scenarios and then the different technology options. And actually, we can also break those costs down based on the level of existing income. So for low-income countries, low middle-income countries, and upper middle-income countries. So I'm going to draw the results to a conclusion here because we've not got very much time left. But essentially, the baseline social cost for delivering universal service ranges from about $500 billion for 4G to 0.94 trillion for 5G non-standalone, for delivering the smallest amount of capacity that we targeted, so about 2 meg per person in the minimum. Whereas if we increase that to try and hit the 10 meg target that the UN Broadband Commission has tried to push, then we'd be looking at the cost increasing to over 1 trillion in the 4G case and 1.4 trillion in the 5G non-standalone case. So really quite a lot more ambitious. Wireless backhaul generally always proves to be much lower cost than fiber, so that's important. And government policy can have quite a substantial impact on the viability of rolling this out via market-based methods, and can help to reduce the actual amount of public subsidy that might be required in order to plug those coverage gaps. So I mentioned this before, that infrastructure sharing has quite a significant impact. So between 15 to 72% of the cost can be reduced, with the shared rural network being one of the largest cost reducing options. And this goes back to the previous question, which is that while spectrum revenue can be really alluring for policymakers, the reality is that by the time you've extracted that revenue from the sector, if you have also to pay out subsidies in areas because the market overall is unviable, then basically for every dollar that you take, it translates to $1 paid out in subsidies. So there's a few limitations. I'll just emphasize these before we finish. So that's that there's this trade-off between the amount of competition you want in your market and how much infrastructure consolidation. And this is always a key issue with infrastructure sharing strategies. It's quite hard to establish existing MNO debts and available capex, and that's, I think, a key fault with this work. This work is still ongoing, and this needs to be addressed, in my opinion, in order for the results to be really plausible. And we always have data limitations on sites and spectrum. So I'm just going to close by saying that judicious policy choices can actually enable many countries to reach over 90% population coverage viably over the next decade, if those options are actually implemented at the policy level.